Hi, and welcome to part 7 in creating a DLX architecture simulator. Um, in the last video, we went to and we created the write back stage, and we wrote it out, and we can now actually save our results to registers. Um, and after that, we said we were going to implement file I/O so that we could read from a binary file. But what we're going to do instead, actually, is we're going to actually implement the memory for our system. And we're going to do this because it's better to do it now so we can make sure all of our instructions work before we start doing the file I/O. Because once we do the file I/O, we definitely want to write our parser. Um, and it lets us kind of insert some instructions into memory to try to read them and make sure that we actually have everything working before we start getting ahead of ourselves. Um, so what we're going to start with today is we're going to start by allocating our memory, and then we're going to actually start using it and implementing it. So what we'll do is we will open up our state machine.c, and inside state machine, where we initialize the state machine and we get current state and set it up and get current registers and set it up, we're going to want to also implement a memory object, or a memory struct, or however you want to call it, but we're going to need to implement that. So what we're going to start by doing is we're going to start by creating a header file and a source file. I don't want a class. I don't want to be initializing templates either, or not responding. Wonderful. Alright, so add new item, and we'll call it memory handler.c. Oh, that's in the wrong folder. Rename H. And then in here we want to add the memory handler.c. Alright, so here we'll set up our header guards, if and def. And I keep forgetting what I do for header guards. Oh yeah. DLX underscore memory underscore handler underscore H underscore define DLX memory handler H and if. And of course we want to include our lovely DLX sim to give us access to all of our project-wide stuff. And then from here we will include memory handler. Oh, we should spell include right though. Memory handler.h. Alright, so in here we're going to want to go to state machine.h, and we are going to want to add, oh, now with caps lock on, include memory handler, and then we're going to want to start implementing, or start writing out our function declarations. So we're going to want to create a struct, so type def struct memory, and then spell type def right. And then we're going to want to return a memory pointer and call it create memory. And then we're going to want to set a void destroy memory and a memory object. And that should be good for now. So now if we actually go in here, we can go memory create memory, and then void destroy memory. So then we'll go memory m equals malloc, and we'll say size of memory, and then return m. And then what we'll want to do is we will want to, in our memory object, we're going to want to have a word, and we'll call it mem, and we'll set an array. It's an array. So this is going to be all of our memory. And what we're going to want to do is we're going to want to specify that mem equals does this work? I forget. I always forget how to declare arrays. No, I think what we want to do is we want to go word memory equals, actually you can do size. So the number of words we want, we'll say 64 for now, just for an arbitrary number to make sure we get this all right. And then we'll say mem equals memory. It's not modifiable. Okay, so that's why we got to do this. Let's go mem. So now we have our memory. So let's set this to a size in here. So constants define memory size, and W for words, we'll say 64. So we'll change this to memory size W. And then we'll do is we'll create a void print memory M. And this will just be how we print to make sure that we actually have access to the memory. So void print memory. So now we'll go to state machine.c and we'll go memory, set up memory M, or current memory equals create memory, and then we'll just go print memory current memory. And inside print memory, we'll just go for int I equals 0, I is 4, I is less than memory size W, I plus plus. And then we'll go printf %d mem I. So that's just to print out the memory. This will actually be nice to have as a function anyway, so we can actually print out our memory contents later on. So we'll insert a breakpoint there, and that way, like if we get to if we ever want to stop our simulator and be like, oh, what are the contents of memory like? We can print it out and we can see like, oh, hey, it's going to be all zeros, or it's going to be, you know, these. We can see our instructions in memory and all that kind of stuff. So it is going to be a good function to have. We're just kind of using it right now to kind of test to make sure that we're allocating memory. So if we loop through, there was build errors. All of these are not working. Incompatible types. Those are all warnings. Missing type specifier, int assumed. I don't think that's for this. I think that might be an error caused somewhere else. Let's make sure nothing else is corrupted. missing type specifier. We're not missing a type specifier. Oh, maybe we need the... Did I delete something maybe? Okay, I may have deleted that value on accident. So let's go here now. And yeah, so we have printed our values out, which is fine because, you know, they're random, so it's whatever. So if we look here now at our diagnostics, I don't know what this is saying. How much memory has we allocated? Tell me, Visual Studio, how much memory do I have? Memory usage, there we go. Alright, so let's restart. So it's going to tell us how much memory we're using, which I don't even know what it should be, but as long as it stays small, we should be fine. Alright, it's taking a little while to restart this. This is awesome. Alright, you couldn't terminate it. Well, maybe you should stop trying, and I can terminate it. I recently made the switch to Windows 10, not by choice, but by Microsoft's discretion. So let's take a snapshot. Allocations 191, heap size. So we have 72.84 kilobytes of memory. Okay. Hey, we can view the heap. That's nice. So we have 256 bytes from the registers, 28 from the logger, 24 from the state, and 12 from the state machine. And I'm not sure where void is, but that would be the memory. Okay, 4 bytes of memory. Alright, so I guess that's okay. So we'll delete that, and we'll stop this. And what we will do is, much like we did with our registers, where we made them global, I think in DLX sim. No, not in DLX sim. Where did we put our registers? Is it in register file handler? Yes, okay, so in memory handler we'll have in memory global memory object. So extern memory. So then what we'll do is inside of our memory handler, or do we do it in state machine? We did it in state machine. So memory, and then we'll say current memory equals create memory, and we'll delete this print memory now, and we'll say or current memory equals null, then status otherwise memory equals current memory. Alright, so now if we go back to memory handler, we can set up some error handling. So if we take a look at our register file handler, we will see that we have our create there, and we're just going to basically duplicate that. So if we go to where is it now? Okay, so memory size in words. So we want define memory size megabytes, define memory size kilobytes, and define memory size bytes. And these will all be kind of factors of each other. So memory size megabytes, we want 64. We will have memory size megabytes times 1024. Memory size kilobytes times 1024. And we will have memory size bytes divided by 4. So that's number of words, because there's 4 bytes per word. So you can have it like that. So those are our 4 different sizes. So now we can go to and create it there. We can go here to memory handler, and instead of specifying our memory this way, what we're going to do is, actually that'll be fine, memory size words, because now it'll be larger. And then we'll set it to there. So we'll go under register file handler, we go create. So we will go if m equals null. Then what we want to do is we want to specify or log it and set the status. So we'll set a status variable, int status equals, so we'll have to go to error.h and add in memory errors and go define memory initialized, set that to 1, define memory success, set that to 0, and then define memory, oh, we didn't spell general all the way. That's kind of disappointing. That's going to create some errors. Init error, maybe. So -1, define memory, no memory error. A little bit of irony there. Define, well, that should be good actually. We don't have file path error. So let's minimize that. Close that. Close the logger. And let's go status equals memory. General init error. Is that what we set to by default? Let's take a look at register. Because register is kind of something we've done already. No, we do success. Okay. Haven't initialized something in a little while. So memory success. So then if memory equals null, status equals mem, no memory error. Actually, let's set this to memory general init error, and then logger error couldn't allocate memory object, and then returns null. Actually, no, I can do that. What we'll do is we'll else, and here's where we'll do this part, and we'll go word memory equals, let's go mem equals malloc memory size bytes, and then if mem equals null, status equals memory, no memory error. So this means we can allocate an object, but we have no memory for the rest of it. And then we'll go logger error couldn't allocate the actual memory. And then we'll go period. Actually, we want to output as well the amount of memory that we are going to be trying to allocate. So let's go sprintf, look up the reference for that, and we'll go char message equals or char message, and then we'll go sprintf message couldn't allocate memory for the memory object. Enough. Couldn't allocate. Let's go %d bytes of memory, and then we'll do put the new line in there, and then we'll do memory size b, and then we'll go logger error message. So this just it's like printing out. It's like printf, but instead of printing to a file, it prints to a string. So I've just never actually used that before, so I could look it up for that time. And in here, we'll also want to set mem or m equals null, or free m, because that way we deallocate the memory allocated there and then return m. So then in here, what we want to do is we want to free mem or m mem and then free m. So that should be good for memory. So state machine creates the memory. So now, if we were to go to main, have our breakpoint there, run it, we'll take another, oh, there's errors. So we'll set it to just the empty string for now then. I don't know why it's giving me that error. Why can't it link it? That's kind of useless. Let's see if we can figure out why that's having a problem. Yeah, there might be another one somewhere else locking it up. Let's try. Let's go to main. See if now we can. Yeah. Alright, so let's stop this now. See if it's now opened up. Well, then let's go look at why it's doing that. Let's see. Good old error debugging. Linker errors are the best errors. So let's go to the location of this. And go there. And there. And let's just delete all these files. Yeah, delete them. Because it's open. Oh yes, skip. Now why is it open? That would be a nice thing to know. Properties. Doesn't say who's got it open. Continue. Cancel. Alright, so cancel. Then what we'll do is we will open our command window. Actually, let's go to CMD and we'll open up as administrator. Get the little prompt. Switch to the drive. And we'll switch all the way through to our wonderful folder location. And we'll delete the file. If we can remember the command. Alright, so now it's gone. Now if we try building it. There we go. Okay, perfect. So we take a snapshot of the memory. And much bigger now. So now if we view our heap, we have 67,000 bytes, which is roughly 64 megabytes, for our so we have 67,000 bytes for our what's it called? Memory. Now why it's not showing up the same way these are, if we go back, as DLX sim exe registers logger state machine, I don't know. See if we can figure it out though. create registers line 9. Let's see what we've done differently there. So if we go to registers, oh, yes, we should allocate this as memory. Now I believe it will show us as our, so if we take a snapshot and then view heap, I guess we're going to view the snapshot. Yeah, memory. Oh, so this actually isn't the memory part. Okay, so that's this part. Actually, let's do a logger here as well. Let's kill this. And let's go logger, and let's call it info. So let's actually move this up here, and we'll say sprintf message allocated %d bytes of memory, and then memory size b, and then we'll print message. And so we can go to our log and view how much memory we've actually allocated. So see what it says. So we can compare that to what the break. So we got an error inside of sprintf. Now why is that? It's exactly the same. Let's stop. Let's try again. Well, what's different now? Let's look up sprintf again to make sure we haven't done anything we shouldn't have. This is weird. Let's try that. See if that tells us an error. Alright, so equals. Let's just give it a size of 128. Didn't want to make that smaller. Let's save that. Maybe now it'll give us a proper. Alright, there we go. Okay, so whatever. We set it to 128, which is more than enough. Alright, so now if we view heap, we have memory 4, and we have void at 67,000 bytes. So now if we go to our folder, and we open up we've allocated 67,108,864 bytes of memory, which, if we open a calculator, we can do the math and say memory handler, so 64 times 10 to the 24 times 10 to the 24. So that's exactly what we had, which is 67,000. So there's actually not 64 million bytes like we'd like to think. There's actually 67,108,864 bytes. So that's all of our memory allocated. So now that we have that done, we can use that to actually access and retrieve memory from our system. So if we were to, so this is now where we get to implement our program counter and all that kind of stuff. So let us take a look here. Let's implement our program counter now. And that's how we're going to actually loop through the memory here. So let's stop this. Let's open up our state machine.c, state machine.h, and let's create a dword program counter. And in our state machine, once everything's been initialized, we will set program counter to equal 0. And then in each cycle, what we will do is we won't want to update every cycle. So this can actually be forever now, because we'll terminate it in a different way. Actually, no, let's leave that there for now. Equals 0. So what we're going to do is we're going to want to anchor or kill this when we get like a halt or whatever. But for now, we'll do that. So process state, we are going to want to increment our program counter after we do a fetch. So inside instruction fetch is when we're going to want to increment our program counter. So our state machine, so process state, if we go to state handler and we go to process state, we can switch this to a dword, and we'll do a dword increment equals 0, and then we'll return the increment. The reason we're doing this is because we're going to set cycle counter plus equals process state, and then we'll go to state machine.h or state handler.h, and we'll set process state to be a dword. So that's all good. But now what it's going to do is it's going to return only if it fetches. So if it fetches something, then we'll say dword or increment equals 4. And that will be 4 bytes. Yes. Yes, okay. And then what we'll do is we'll set fetch. So we'll change that and delete that and say word instruction equals memory. So we don't have access to memory, and that is because memory. How do we have access to memory? Memory should be, is everything else in DLX sim? No, everything else is not DLX sim. So state handler does state machine.h have, how does state handler get the registers? State handler.h, does instruction handler have access to the registers? No. Where does it get access to the registers from? I don't know. Let's include it in here then. Include memory handler. And then what we'll do is we'll go to state handler, and we will say memory. Actually, let's try, maybe I had it wrong. state handler, go word memory. No, okay. So let's go add it in, and we'll go equals memory mem, and we want program counter. Oh, no. Program counter is going to be passed in. So let's say dword PC. Actually, what we can do then is we can say, instead of returning increment, we can, well, actually, yeah, let's do increment still. Well, dword increment 0. Actually, let's go new PC equals PC, and then new PC plus equals 4, and then return new PC, and then in here we'll pass fetch in the PC, so dword PC, and then PC. So now, if we go back to statehandler.h, change, oh, it'll have to be up here actually. Change this to a dword, and then here we will have to have dword, and then in statemachine.c we will pass in the program counter. So now if we insert a breakpoint here and we remove the one in main, which you already have not, now if we run this, now what's our error here? Access violation. No, that's not what I want. Why do we have an access violation? Unable to read memory. Well, what do we have in memory handler? So this is why it's a good thing to test this. If you go to memoryhandler.c, oh yes, because we never actually assigned the memory to m. Mem equals mem. Alright, there we go. So now if we run this, perfect. So let's take a snapshot of our heap. Still more or less the same size. Yeah, perfect. So it still goes to the void since we don't have a type on it, which is fine. We don't need a type on it. But if we go to cycle counter 4, okay, can we view this memory? No, we can't. But, so, anyways, we would be accessing, where is our breakpoint? Main. No, statemachine.c. Yes, here we go. So, we would be accessing number 4. And if we continue, that's cycle counter, not program counter. Alright, so let's try this again. So why does cycle counter equal 4? Oh, because it's in hex. That's right. No, that doesn't make sense. Oh, because we're incrementing program counter, not cycle counter. Whew. That was dangerous there. Alright. So perfect. Cycle counter equals 0. Program counter equals 4. We continue. Program counter equals 8. So let's add a watch. Program counter. So now if we continue, Oh yes, so it's trying to access something that doesn't exist. Yeah, because data is something that we don't know exactly what it is. We haven't actually processed the instruction because we grabbed memory that we're not sure what exactly is in it. So that makes sense, and that's why it's good to have. That's why it's not good to let things run by themselves, because that's how you. Luckily, this machine's pretty good. The compilers are pretty good that they won't let you do anything stupid, but this is how you do stupid things. So luckily, we didn't break anything. Everything's still working, but that's definitely how you break stuff. Um, so now we have the ability to fetch instructions from memory. Um, Now we would have to write next time the actual memory access value, which will depend on the instruction which memory we access. Um, so that would be determined in the execute, and then from execute we would execute like any addition onto the operation that we need to do, or any addition onto the any operation we need to perform on the address, and then we would use the address to actually to get the value. So for now, what we can do is we can say dword or address. Actually, let's not do that now. We have to add all that in, so that can be next time. So now we have our memory in place. We get our instruction from memory now instead of from just hand coding it in. So next time we can actually take our instructions and we can insert some instructions in and then execute them by reading them from memory instead of reading them from hard-coded values. So we can actually insert a couple instructions and make sure they're actually updating by running them and then printing out the registers. So that's what we'll do next time, as well as write the access memory function so we can actually load and store data. And then from there, we should have everything in place to actually implement instructions. And we can start implementing more of our instructions. And then we can actually start writing actual source code files that we'll interpret and run. So until next time, happy programming.